Hello everybody, welcome to another great day of multivariable calculus here. We're going to talk about quadric surfaces. Look at my head over here on this side. So there's a couple types of surfaces that we have. You should know about a sphere. We've done that before, and then a plane. We're going to talk a little bit about cylinders, but not going to focus on it too much because cylinders are going to be parallel to either the xy plane, yz plane, or xz plane. And cylinders are not always circular cylinders. Like here's a circular cylinder right down here, but here's a parabolic cylinder. Cylinders just extend out infinitely. So just a little bit of that, but we're going to really focus on brand new types of surfaces. So here's the general form, and boy, is it a lot. It's ax squared plus by squared plus cz squared plus, and you get the idea. And kind of mix all the x's and the y's and stuff like that. So there's a lot going on there. But you do need to know what some of these are by classifying them. It's really helpful as we move into the course when we start taking the rate of change of everything and trying to find volumes of whatever. So here's three. I think I got 6 of them here for you. So this is an ellipsoid. All these A, B's, and C's might be a little bit different. It kind of looks like a football a little bit. Big characteristic here, no minus sign. Hyperboloid of one sheet has just one minus sign. Hyperboloid of 2 sheets has 2 minus signs. So hyperboloid here, if you notice, they do connect in the middle here, whereas the 2 sheets, they don't connect because it's 2 sheets. All right, so these are all kind of mix and match with each other. We do get elliptic cone here when we have z squared equals, so if they're all squared, and it's just z squared, no term in front of it there. So there's no linear terms, it's elliptic cone. If we just have z equals, that's a little bit different. We have elliptic paraboloid. It's elliptic based on the ellipse. Should kind of look like an ellipse. If z was 1, it would be an ellipse. So it's got 1 linear term and 2 quadratic terms. And then if we do a minus sign right there, that gives us a hyperbolic paraboloid, also known as a saddle. A lot of what we do in this course, I'm telling you right now, the saddles appear a lot. So it's really helpful to know what all these look like. There are characteristics in here, so I think these digital pictures are great. I will, when I get to this, for example, right here, sketch these. Really, I'm not going to sketch them for you, but I'm going to use technology to sketch them for you. Okay, so all we're going to do is we're just going to identify what is going on here, what these things look like, and then we'll go ahead and sketch them using technology. So for this first example here, we do have to make this look like one of our formulas that we have here, but since these are all squared and all plus signs, it's really looking like it's going to be an ellipsoid here. So when I divide everything by 36 so that we can get the 1 on the one side there. So I'll zoom in here. So we're going to divide everything by 36. So we're going to get x squared over 9 plus y squared over 4 plus z squared over 36 equals 1. So this is an ellipsoid. It is centered at 0, 0, 0. So it's centered at the origin here. In the x direction, ellipsoid is going out 3. In the y direction, ellipsoid is going out 2. I just know that because these are squareds. So 3 squareds, 9, 2 squareds, 4. And then so in the z direction, we're going to get 6. So I just used Desmos 3D to go ahead and sketch this. So it's this one right here. Okay. I don't want to zoom in too much. So there you go. So in the x direction, I mean, you can kind of see if I were to go up here. So in the x direction, it's going out to 3. So 1, 2, 3. Here's x. And the y direction is going out 2. And then if I can make this on there we go, the yz plane, you can. I guess they don't give you coordinates to tell you how far. Oh, if you zoom out enough, it might give you something, but it doesn't. It's going to go up 6 right there. So there you go. That's it. So you sketch that. I won't. I believe in you. I feel like I probably should. So in the x direction, 3, the y direction, 2, the z direction, 1, 2, 3, 4. And there we go. So it just kind of looks like a little bit of a football here. So this is why I don't draw this for you. Okay, that's what it looks like. I mean, on my picture I have on my notes looks much better because I can. Drawing on this, it's solid green. It's not like I can do light-handed, so oof. Oof and a half on that one. On this one is going to be linear term and then two squares terms. So it's going to look like this one right here because they're adding. So this is an elliptic paraboloid. This one, instead of being the z equals, so this is opening up in the z direction, this is going to open up in the x direction. So this is I'll do a different color. Elliptic paraboloid. Wow, I can't spell paraboloid. Vertex is 0, 0, 0, and this is opening along the x axis. So if I were to sketch this, and then I'll show you like what it really looks like, you'll see how great at drawing I am. So here's the x-axis. It's going to open up like this way. Okay, and it should be a little bit fatter on the y side. It does not look like it is. It should be a little bit fatter on the y side. Oof. Oof and a half here on this drawing. I'll do better by showing you what it actually looks like. So see you later. That's the old one, and then here we go. So there. See, we're a little bit fatter on the y side. Opening up twice as fast as is the z side. So opening along the x direction right there. So there you go. That's what that looks like. And then our last one here, I have one minus sign, everything's squared, so it's going to be I'll show you, a hyperboloid of one sheet. So the minus sign here is z, so it's going to go opening along the z-axis. Our minus sign for over here is going to be y, so this is going to open along the y-axis. And actually, let's divide everything by 9 here. So that this equals 1. So I'm going to get x squared over 9 minus y squared over 9 plus z squared over 9. So hyperboloid. Did I even spell hyperboloid right? No, it's an O with an I. Oy. I'll fix it. Of one sheet. And this is going to go along the y-axis. So if I were to sketch this, it's going to open up along this way. All right, and what does that look like? That looks like, let me undo that last one. Let's go do this next one, and there you go. I mean, this opens up. It just looks a little curvy. Oh, don't do that. It just looks a little curvy here because it's trying. The program confines it inside this box, so that's why. But there you go. There's the hyperboloid of one sheet. Next up, we're going to classify and sketch this. This is not in our normal forms that we've seen of those 6 different ones, but this is. We need to make this into our form that we're used to here. So what I'm going to do is I'm going to complete this square. Organize your x's and organize your y's and organize your z's. So I'm going to go x squared minus 4x plus something plus 2. So I need to make sure that's a y squared in front right there. So 2y squared plus, instead of 4y, it's actually 2y, because 2 times 2y gives me 4y. Plus, I'll figure that part out in a second. Plus, I have z squared minus 2z plus something, and that's going to equal, if I subtract 3 from both sides, negative 3, and I got to figure everything else out here. So, clearing the square, I did go over this in another video. You're going to cut the b term in half and square it, so this right here is going to end up being a 4, so I'm going to add 4 over here. The z, I'm going to skip the y here in a second. Actually, no, I'll do the y one right now. This is going to end up being 1 right here. But since that's 1, I'm actually have to add 2 times 1 to both sides. So this is going to be plus 2. And then for this z, cut that in half, square it, and end up with 1. Okay, so you're going to end up with is that 4 on that one side? So if I go ahead and flip the square, I'm going to get x minus 2 all squared plus 2 y plus 1 all squared plus z minus 1 all squared equals 4. And so everything's squared here. This is clearly going to be an ellipsoid centered at 2, -1, 1. And let's go ahead and find out what this looks like in each direction by dividing everything by 4. I'm going to get x minus 2 squared over 4 plus y plus 1 squared over 2 plus z minus 1 squared over 4 equals 1. So this is an ellipsoid. Centered at, what is it, 2, -1, 1. And in the y direction doesn't go out as far, so I'm going to go back to my, actually I have this one already. So there you go, see how it's centered off a little bit right there? It's a little bit wider towards the, or sorry, the x's and the z direction a little bit wider, it's a little bit shorter, narrower around the y axis, because it's going to go out √2 in each direction. Oh boy. For the y's on that one. So there you go. That's me sketching it for you. All right, last little itty bitty thing here to do with quadric surfaces is just, if you remember from calculus, you can actually rotate figures to create volume. So to get the surface of revolution, they're just talking about how if you were to rotate, you can get these shapes as well. So if you revolve anything about the x-axis, it's going to be y squared plus z squared equals, and then that function in terms of x being squared. Same thing for the y-axis, z-axis. So real quick here, find the equation of a surface of revolution formed by revolving the graph of y equals 1 over z about the z-axis. So since we're going about the z-axis, we need r of z. So r of z is going to be 1 over z, because I'm looking at this right here. Okay? So now if I do this about the z-axis, I'm going to have this equation right here, which is going to be x squared plus y squared equals 1 over z, and that is all squared. And that really is it for the axis of revolution.